Alright, hello. Welcome back to video 2, or episode 2, or lesson 2, or lecture 2. Professor Dam is back with another. Okay, I'm back with another lesson. So, previously we finished up with atomic radius on ions. So now we will continue on with ionization energy. Now, what is that, you might ask? Well, ionization energy, it is the measure of difficulty in removing an electron from a given element. So, one important thing to know is that most elements, except for the transition metals, most elements have the ideal electron configuration of some noble gas, of the nearest noble gas. So if you look at the electron configurations that we did the previous video, you can see that the electron configuration of this one is the noble gas helium. That is 1s2. And the electron configuration of this one, 1s2 to be 2s2 to p6, is the electron configuration of neon. So our electron configurations, the ideal ones for most elements are trying to achieve the configuration of the noble gas. So, for the example, everything on this side, all the way on the left, they're trying to lose an electron, because this here, let's just say here, so this here would be 3s1, but if it loses an electron, it would lose the 3s1, and then it would be at neon's electron configuration. And then something like oxygen, let's just iodide. So iodide, it has a negative charge, so it has one more electron than proton. So that means it gains an electron. So it gains an electron, and so this 5p5 would turn to 5p6 because it gains an electron, and 5p6 would be xenon. Would be the standard xenon electron configuration. So that is something important to note for this new topic. So ionization energy. So just put the rules. Okay, so metals. Oh no, not metals. Any elements that form cations where electrons are lost because they're positively charged, so there should be less electrons than protons. For these, it is easy to remove the electrons. But for elements forming anions, these are electrons gained, it is hard to remove electrons. Electrons. Let's color code this real quick. This color, I guess. I think. Let's see. Tips. Sorry about this. Alright. So, actually, no, it's important to note, not tip. So, it is hard for anions to remove electrons because if you look over here, anions are trying to gain electrons in order to establish the noble gas electron configuration. So, like for example here, oxygen needs to gain 2 electrons. It needs to gain 2 electrons since it's also in the 2 minus charge category. So there would be 2 more electrons than protons. So it has to gain 2 electrons in order to establish the ideal noble gas configuration, electron configuration. So if it's trying to gain electrons, taking electrons from it would be very, very difficult because it's not going to like that. It's going to want to gain electrons. On the other hand, if you look at elements that are that form cations, like calcium wants to lose 1 and then 2 electrons to argon to go to argon's ideal electron configuration. So taking electrons from it, removing electrons from calcium is easy because it wants to lose electrons in the first place. So basically all metals, since all metals are cations except for hydrogen, all metals want to lose electrons. So it's very easy for metals to do that. So let me just put that here. So this is metal, non-metal. And let me just write down the thing I said earlier. So it's down on paper, important. I mean, it's just, no, it's important. So, elements in ionic or form ions in order to obtain the electron configuration of the closest noble gas. And this is ideal for every element except for noble gases because they're already at the ideal, so they don't have to do anything. All right, so keeping that in mind, keeping that in mind, okay. In general, the ionization energy increases, which is ionization is the difficulty, so it's more difficult to remove an electron as it moves toward the top, and right of the periodic table. Yeah. Top, I'm not sure why it increases when it goes up. If anything, it's just, I would assume that it is because it has fewer and fewer electrons. So it quote unquote treasures the electrons with more value. That's what I would assume, but don't quote me for that. But yeah, that's the general rule for ionization energy. So now we will be moving on to electronegativity. So, here, electronegativity. So that is the measure of elements of an element's desire to gain an electron. So, elements forming cations have a low electronegativity as they prefer to lose electrons, as we know from just up here, just earlier. They want to lose electrons in order to obtain the electron configuration of the closest noble gas, which is ideal for them. So they would not want to gain an electron. They don't have a desire for it. So the elements that are forming anions have a high electronegativity. Right, and then just like how anions are, so to put this into another term, this also means metals over here, and this is most non-metals. And I put most for a reason, because non-metal noble gases have zero electronegativity. And now to finish this up, in general, electronegativity increases toward the top and the right of periodic table. That doesn't make sense, right? this makes sense because basically, in a way, ionization energy and electronegativity energy is measuring kind of the same thing. How ionization energy is measuring the difficulty in removing an electron from a given element. So it's how difficult it is to remove an electron. So if they desire to gain an electron, like electronegativity, they will have a very high desire to gain an electron would also result in a very high measure of difficulty in removing an electron, because they don't want to remove an electron, they have the desire to gain one. So it makes sense that both of the general patterns or trends for electronegativity and ionization energy are the same. And I didn't talk about I didn't explain why anions have high electronegativity. So anions need to gain a few electrons in order to get the electron configuration of the closest noble gas. So they will have a desire to gain electrons in order to reach their ideal electron configuration. And yeah, so our choices are so here's like a little example exercise for us. So here's an example. So our choices are lithium, beryllium, boron, fluoride, and neon. So questions are, which one is a metalloid, and then which one's a halogen, alkaline, earth metal, which one is inert, inert. Okay, let me put a little tip here. Inert basically means it's not it doesn't participate, not participating in chemical reactions. Which one is in sublevel P1? It could be any energy level, just the sublevel has to be P, and then it has to be only one electron in it. Which one is a metal with no unpaired electron? Which one has 3 valence electrons? Which one has the largest radius? Largest ionization energy? And largest electronegativity. Alright, so before I start explaining, feel free to pause here on the video and try to answer the 10 questions, and then you can see how you do. Alright, so a metalloid, kind of just have to look at the periodic table with like categories. But the metalloid in this little choice list would be boron. Halogens. Halogens are anything in the group. I don't remember the. I believe it was 7A. Yep, 7A, which this chart does not have it. So basically, it's 1, 2, 3, 4, 5, 6, 7, 8. These are all A's, and then these are all B's down here. So 7A. So that means like fluoride, chloride, bromide, iodide, or ion. Wait, fluorine, chlorine, bromine, iodine, etc., etc. So those are halogens, and so in this choice list we have fluorine. Okay, and then alkaline earth metal. Our alkaline earth metal is beryllium. Since alkaline earth metals are in group 2A, and that is beryllium. Let me just add A. Right. So inert. So the only elements that are inert, that are not participating in chemical reactions, are noble gases. So the only noble gas in this list would be neon, and they just don't participate in chemical reactions because they're not interested in sharing electrons. They don't want to give away electrons or take electrons, since they are at ideal electron configuration. Right, and P1 would be boron again. A metal with no unpaired electron would be beryllium, because it is in the two P's, and it has 2 electrons in it, and there's 1 orbital, so that means it's unpaired. 3 valence electrons, that would be boron once again. Largest radius, so remember, largest radius, it increases as we go down and as we go to the left. So down and left. So out of all the options we were given, it would be lithium, because they're all in the same period, just in different groups. So lithium is the closest to the left. But here is a very important thing to note. For example, if you were given lithium and magnesium, and you were asked which one has a larger radius, it would be tough because they're diagonal from each other. They're equidistant from the bottom left. So, but something important to note is that the energy level rule is the strongest. Is like, it determines the radius by a large factor. So even like if you have lithium all the way over here, and then you have argon all the way over here, the energy level would make it so that argon has a larger radius. So down is always the rule, and then if it's on the same row, then it's to the left. Just remember that. So I'll put that for you. So radius always highest Yep, there we go. Okay. Now continuing on our final two. So the largest ionization energy would be neon, because it is um it is the most top and right trend. But if you don't look at the trends and you want to get an explanation, well, so we know that anions have a very high difficulty of removing an electron, but neon has the highest difficulty because of how it is already at ideal state. It's already at the ideal state, so it would be very difficult for it to be pushed and shifted out of the ideal state, compared to even fluoride or fluorine, because fluorine is not at ideal yet. So that's why neon would have the largest ionization energy. And largest electronegativity, we know that noble gases have a zero electronegativity. So it would be whatever is the most top right, excluding neon, and that would be fluorine. And once again, it's almost at its ideal state, as long as it gains one more electron. So its desire to gain that last electron is the largest. It really, really, really wants to gain that electron in order to go to become at its ideal state. So final answer would be fluoride or fluorine. I apologize. I keep calling them by their ionic names. Yeah. Alright, so that will end our video 2. I have no clue how long that was. But hopefully that wasn't so boring. Hopefully my voice isn't so boring. But as always, just if you have any questions, message me. Feel free to message me. I will be more than happy to help you. I'll try my best to help you. If I can't, I'll look it up and try to help you then. But yeah, see you in video 3.